perfect segue. So we did a study on this cost performance of Graviton 3 versus Graviton 2. And so the idea of cost performance, we're thinking about not just is it cheaper or is it faster, but some combination of the two, where sometimes we're willing to pay the same amount and have it go faster, and sometimes we're happy to keep the performance steady and pay less. So when we're talking about that cost performance ratio, it could be either one of those cases or somewhere in the middle. Looking at the study that we did, and this is on our AWS Made Easy page, we posted about it yesterday. So they did compared similar workloads on 3 different instance types. So this is, the yellow here is the C6G, so that's the older Graviton, the Graviton 2. The blue is the Graviton 3, and then the red is a similar instance but with Intel Xeon. And the vertical axis here is seconds to complete the same amount of tasks. So I guess what a really cool finding is, if you just simply switch from Graviton 2 to Graviton 3, with the finding here, 25 to 30% better, with no transition effort, no porting. It's the same architecture. It's literally just flipping that switch. It's a really neat, pretty neat.
I would just add a caveat to that. So if you are typically running an application that is based on a virtual machine, so languages that run on Java, Ruby, Rails kind of architectures, or Python, or Node.js, ones that run on some kind of a virtual machine for interpretation, you should generally not have a problem switching from x86 to ARM. The only places where we run into some complications are scenarios where you have some libraries that have a native core. There are some Java libraries that are written in JNI, basically C++ implementations under a Java wrapper. Scenarios like that will require you to recompile the native core part of it so that it's compatible with ARM processors. For the most part, you usually don't encounter those kind of scenarios anymore. So you should be able to relatively easily take your x86-based application and port it over to ARM pretty easily.
Yeah, in fact, there was one of the talks at reInvent. I forgot the name. I'll post it in the show notes. One of the talks in reInvent, they did a study on the Graviton transitioning to ARM, and they found it took many dev teams about a week on average. So like you said, occasionally there's these underlying dependencies where usually it's a matter of tracking down the ARM-based dependency, maybe switching one of your compiler flags. So yeah, on something like Python or Ruby where it's interpreted, not a big deal, but at something lower level, you'll have to dig deep. But usually these things have been solved and documented. The savings are so good that the whole community has an incentive to chase this.
No, absolutely. The price performance improvement is to the order of 40% or greater, depending on your somewhere between, I'd say, 20 and 40%. But the other key thing I think for our audience to understand is that when we deal with AWS, we are dealing in terms of vCPUs, right? And that's the fundamental unit that you purchase. And one would think that these are apples to apples comparisons, but they really are not. The way vCPU is computed on ARM versus the way it's computed on the x86 machines is fundamentally different. When you look at x86 architecture, each core is a hyper-threaded core. That means you can run 2 threads on each core. So when you buy a vCPU or when you reserve a vCPU on x86 architecture, what you're effectively getting is half a core, or you're getting 1 thread. If you get a 2 vCPU instance, you effectively get 1 core at that point. On ARM, given that ARM is single-threaded on a per-core basis, what you get is an entire core. So even if you have the state-of-the-art, processor on x86 that's running at near 5 gigahertz, in effect, what you're getting is only a single thread out of 2 threads that are running on that core on x86. So it is whatever you get on that 1 thread. You also have the overheads of managing the threads and the pipelines there. though Intel and AMD have gotten pretty efficient with managing those pipelines. On the ARM side of things, you literally get the dedicated core that processes your single thread, and that is your vCPU. So there is a fundamental difference in the units. Even though you're talking about vCPUs, it is not an apples to apples comparison when you actually look at what you're getting out of the processor.
That makes a lot of sense, right? There's these, as the processors are getting more and more and more specialized, it's hard to imagine that this one number can distill everything that you'd need to know. And so that's why we did this study. Again, the link will be in the show notes, and it's on our AWS Made Easy LinkedIn page. The idea is, here we go. I guess the main takeaway, it said Graviton 3 improved performance of single-threaded applications over Graviton 2, but shines best in these parallel applications, right? Because in parallel, you get to take full advantage of all of the cores. And then also, I guess here's a neat kind of summary statistic. From 2 to 3, instantaneous speed improvement while costing only about, the speed improvement is on the order of 20 to 35%, whereas the cost improvement is about 6%, 6% increase. So that's pretty exciting. And this, other people have done some testing and ran into similar orders of magnitude speed ups. And I guess one other thing I want to say about the Graviton is that they focused on real workloads. So these aren't, what's the right word? Kind of artificial specs based on contrived scenarios that you wouldn't ever actually encounter. That these are real, these are your databases and analytics and ETL pipelines, the bread and butter stuff that we're all doing every day. So it's pretty exciting.
Yeah, and from our experience working with the Graviton team at AWS over the last few months, it's remarkable. Every little optimization that they've done and they've worked on is based on a real world workload, like you said. It is not hypothetical. They are not randomly trying to optimize everything there. They're literally looking at all the standard instructions that are basically going into the processor, and they're optimizing those pipelines. Every time they encounter a new scenario where they find something being slow, they look at what kind of instructions are going in. They're optimizing those and making them available to customers. So they are, like you said, working on real world workloads and not hypothetical scenarios or made up benchmarks that you invariably see in a lot of scenarios.
Perfect. So let's. Do we have anything else to say about ARM before we talk about the other big CPU in the room, about EPYC?
No, I just say get on ARM as quickly as possible. This is the bet you want to make. Like I said before, the runway for performance improvements on ARM are significantly greater than on the x86 architecture. At this point, AMD and to some extent Intel, they are literally fighting physics to the point where they are trying to figure out how not to melt the CPU as they are kind of increasing the number of cores on every little CPU, and the TDP is kind of reaching insane level at those 5.5 gigahertz clock speeds. They are having to make trade-offs like decide what are going to be efficiency cores and decide what are going to be performance cores, because if they made everything a performance core, they would literally melt the CPU. So they are fighting physics at that particular place. And when you look at the trade-offs that the likes of Amazon have to make with Graviton on the ARM side, there's just so much headway. You can go up to 96 cores that the architecture supports. You can go from 2.5 gigahertz on a core up to 3.1 and get a massive boost just out of that. You already have 3 sockets per motherboard. So they have so much more room for performance improvements over the next few years compared to x86 that really is the bet you want to make. So please go ahead and try it out, see if applications work there. It's more performant and saves you tons of money.